Hello everyone, and I'm Aravind, and I'm from Group 9, and my group mates are Mohammed Saeed, Junaid, and Rishwant. And I'm here to present the third progress update of our project titled Real-Time Weapon Detection Using Computer Vision. So our project has moved from idea to implementation, and in this update, I'm excited to show like how we took our project beyond just training and testing and made it work in a real-time environment. And I'll walk you through a quick recap of where we left off in the last update too. So the main goals of this phase, how the system now works in real time, a live demo we built, some observation from the test, and finally the challenges we faced while making everything work smoothly. So let me move on to the second slide. So let's take a quick look back, like in update two, like we transitioned from our custom PyTorch model to using YOLO V5. So this was a lighter version of the YOLO V5 object detection model, and we chose it mainly because it offered a good balance between accuracy and speed, so which is important for real-time application. So we trained this model on a dataset of around 715 weapon images. The training and validation losses steadily decreased, which indicated that the model was learning well. We also evaluated the model using a confusion matrix and a F1 score from the matrix. So we saw that it could detect some weapons correctly, but there were also quite a few false negatives and false positives. For example, it sometimes missed weapons entirely or incorrectly labeled background objects as weapons. So the F1 score we achieved was around 0.40 at a confidence threshold of 0.24, which showed that the model had potential but still needed improvement, especially in real-time conditions. Overall, the update 2 focused mostly on training, evaluation, and offline testing, while we didn't explore that as how the model would perform in a real-time setting, which became the focus for update 3. So, objective of this update. The objective of update 3 was very clear. We wanted to move beyond static images and offline evaluation and actually implemented the system in real-time environment. That means instead of feeding test images to the model and waiting for output, we wanted to see if we could connect it to a live video stream or a webcam and get the system to detect weapons on the fly in real time. So the real challenge here was not just running the model, it was making sure that it could process multiple video frames quickly. It didn't lag or slow down the system, and that it could still detect weapons accurately even with real world variability like lighting, angles, and motion. So this requires integrating the model into a real-time pipeline where each frame from the video is treated like an individual image and passed through the model continuously. So overall, this update was all about bridging the gap between research and real-time applications. So the system workflow. So these slides shows the full workflow of the system after implementing real-time capability. First, we start with an input source, which can be either a webcam or a video file. So the system captures this video stream and breaks it into individual frames. So each frame is then passed to YOLO V5 model. The model performs object detection on that frame and checks if it contains any known weapon classes such as guns or knives. So if a weapon is detected, the model returns a bounding box and a label with the detection confidence. So these bounding box is then drawn on the frame and the label is displayed in real time. So just like a live feed with highlighted threads. So this process repeats continuously for every frame, so which gives the effect of a live detection system. What's important to note is that this all happens most almost instantly, like which makes it usable for scenarios where fast response is critical, like in school, airports, or some critical condition, public places. So the video in and then to the frame extraction and detection, display with the bounding boxes is all happening in a loop. So this is the demo. I'll just play the video. So in this demo, we used a webcam feed and some test videos to check how the system performs, as you'll see in the video. The model detects weapons like guns and guns, particularly in this video, and draws accurate bounding boxes. You can able to see from here. The thing was seeing a system respond almost immediately. As soon as weapon was visible, it was detected and highlighted, like here. So these confirmed our system was not just working in theory, it was now operating in real world condition like these. even though this is still a student level project, but we were able to build a demo that could someday be adapted for use in surveillance systems provided. Like we can improve it further. So let me move on to the next slide. So the results and observation. First, the system was able to detect weapons accurately in most cases, especially for guns. The detection was solid. Performance was best in good lighting conditions, so clear videos and steady camera views helped the model make reliable predictions. So we also noticed some false positives. For example, tools or remote controls were sometimes misidentified as weapons. So this is something we expected, but can work on reducing with more data and fine tuning. So this system could process multiple frames per second, and while it was not perfect, the speed and responsiveness were acceptable for real-time student project. So overall, the results were positive. We were able to achieve our goal of live detection and confirm that the system can detect weapons in real time. The challenges we faced. Finally, we did face a few challenges while building this system. So first, setting up the real-time pipeline was technically more complex than just running inference on test images. So we had to make sure frame capture processing and display were well synchronized one. Second, the system performance depends on a lot of the device it runs on. So on laptops without GPUs, I mean without powerful GPUs, the frame rates and drop. So it literally slowed down the process. Third, we struggle with lighting and background clutter. So that's the important issue we face. So in dimly lit scenes or when there were too many objects in the background, the model's performance decreased actually. So it's automatically detects something else. Lastly, false positives were a challenge. Things like mobile phones, metal tools, or even black colored objects sometimes triggered incorrect detection. So these are real world issues, and while we can't solve all of them immediately, but we now know where to focus our improvement efforts in the final thing. So to wrap up, like in this subject, we successfully integrated our model into real-time video detection system. So we created a working demo and tested on in a webcam feed. So the results were very promising, and this is sufficient for the project. So the accurate detection, real-time speed, and the function system also very promising. So we learned that what we need to be improved. So especially in terms of lighting, false positives, and hardware optimization. So thank you so much.